Hello. This week we're going to be covering Chapter 7. We'll also be covering Chapter 8. I'll continue on with that here when we finish this. In this lecture, we're going to be discussing kinetic energy as well as work. These are concepts that come about when you are attempting to describe what the capacity is for a particular system. And how do these concepts relate to what we've already learned so far? So energy is going to be required for any sort of motion. It's technically a scalar quantity that's assigned to an object or a system of objects. It can change from one form to another. For example, you could be looking at kinetic energy changing into potential and vice versa. It is conserved in a closed system. In other words, the total amount of energy of all types is always the same if you put the sum together. Now, obviously, it can change form from one form to another, but the total amount is going to remain the same. So for this particular chapter, we're going to discuss one specific type of energy, and that's energy of motion, or kinetic energy. We're also going to discuss the method of transferring energy, and that will be called work. So, kinetic energy. The faster an object moves, the greater its kinetic energy. And if an object is not moving, then it has no kinetic energy. So if we're looking at objects with a velocity that's well below the speed of light, then we're going to be looking at a kinetic energy that's going to be defined as 1/2 of the mass times the velocity squared. The unit of kinetic energy is going to be the joule. And you can see there in equation 2 that it's going to be 1 joule represented with J. It's also going to be 1 kilogram meter squared per second squared. Another way to look at this is going to be, it's going to be 1 Newton meter, if you're familiar with the units for newtons. So, for example, energy released by 2 colliding trains with given weight and acceleration from rest. So we're going to find the final velocity of each locomotive. We can do that by using one of our kinematic equations here. V squared is equal to V naught squared plus 2a times the quantity x minus x naught. We're going to, let's see, I need to admit here. Hello, Giselle. Well, glad you can make it. Don't know exactly what you've caught up to this point. Probably not much. I hadn't really made it too far into the lecture. I can go back and start again if you would like.
No, it's okay.
Okay. All right. Like I said, I really hadn't made it that far. This chapter is going to be the discussion of kinetic energy, and it's going to be discussing how that kinetic energy is pushed to other objects, and that's going to be done through a concept called work. So that's the gist of what I had been discussing up to this point. How are things going overall? Any issues or problems that we need to go over?
No.
Okay.
Good.
Braden will not be able to make it tonight. Tracy obviously will not be here. And he had asked how to submit the lab report, and I just told him to email it to me.
Okay.
We ought to be good there. My best efforts will be made to try to grade that over the weekend. And that's pretty much how those will go. So here I was discussing the problem with kinetic energy and how much energy might be released by two trains that are colliding with a certain weight and acceleration. So as we were going through here, we were attempting to find the final velocity of each locomotive. We were doing that with a kinematic equation. We knew what all of these particular values are. We knew what this distance is from where they started out to where they ended up. We know what the acceleration was, and so we put all of that information into the problem to find V naught. We then take the square root and we figured out how fast these trains were moving. And the reason we need that is because our kinetic energy is defined as 1/2 times m times the velocity squared. If we know how much a train weighs, then if we divide that by our gravitational acceleration constant, we can determine what the mass is. So to find the kinetic energy of both trains which are colliding, we take assuming both trains weigh the same and both are moving at the same velocity, we just take 1/2 mv squared and multiply it by 2 because we have two trains. We get mass and then times the velocity squared, and our answer comes out to be 2 times 10 to the 8th joules. So energy will be measured in joules in the SI system. All right. So what we are going to do now is apply a relationship between a force and the work done on a particle. And we're going to do that by taking a dot product. Account for changes in kinetic energy by saying energy has been transferred to or from an object. In a transfer of energy via a force, work is done on the object by the force. So work, which is represented with W, is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. So that last sentence there is something to bear in mind as we go forward. Energy transferred to the object is considered positive work. Positive work, you can just assume that you gain energy with it. And anything you lose energy with is going to be considered negative work. So to do work on an object, energy must be transferred. So throwing a baseball does work. You're transferring energy to the baseball. Pushing an immovable wall, while it may make you tired, does not constitute work. And the reason is that the wall never moves. You've got to have some sort of distance be covered in order to, in a physics sense, be classified as work. All right, so start from the force equation and one-dimensional velocity. So you've got the force in the x direction is equal to mass times acceleration in the x direction. Then you've also got the velocities and acceleration in the x direction in the next equation. If you rearrange into definitions of kinetic energies, what you find out is that the 1/2 mv squared, your final velocity, minus 1/2 mv naught squared, is going to be equal to force times the distance. So the left side is going to represent how much change in energy you've got from the end to subtracting the beginning. So the work is therefore going to be the force times the distance. Again, we had defined work as the change in energy. So to calculate the work that a force does on an object as the object moves through some displacement, we use only the force component along the object's displacement. So the force component perpendicular to displacement does 0 work. So in other words, if you have something orthogonal to the direction that an object begins to move, that is not considered to be doing any work. So if you have an angle between the force and the displacement, if you take the cosine of that angle and multiply that by the force times the distance, what you're doing is you're getting an idea as to how closely that force and that distance are being correlated with one another. You're just wanting the component of the force that lies along that same vector as the displacement. And if you're going to write this as a vector, you're going to write as the dot product of F and D, force and displacement. So the notes on these particular equations is that the force is constant, the object is considered to be particle light, and that work can be positive or it can be negative. So let's take a look here. We've got a bead right there, and it is along a wire. And we're looking at a force on that particular bead, and that force is an angle. So this part right here, let me zoom in a little bit more. So if we're looking at the component of the force that lies in the same direction as the displacement, which is going to be this direction, we're going to want the component of the force that points this way. This lies on a dimension that's 90 degrees from this, and therefore it does not consider to be doing any work because the bead is not moving in that direction. So the bead starts out here with a small amount of initial kinetic energy, and this force does positive work on the bead, increasing its speed and kinetic energy. So it's adding to the kinetic energy of this particular bead. And we can see that as it moves through here. As the bead moves along, it's got a velocity that's greater than what it started out with, which means it's got a larger final kinetic energy. And as it moves from here over to here, and this is going to be considered the displacement. So work has the SI unit of joules. It's the same as energy. And in the British system, the unit is called the foot-pound. So, any questions so far?
No, I think I'm okay.
Okay, all right, good. A force does positive work. In other words, it's going to add energy to an object when it has a vector component in the same direction as the displacement. And it does negative work when the vector component is in the opposite direction. If it doesn't have an application in either that direction or the opposite direction, it's considered to do no work. So for two or more forces, the net work is going to be the sum of the works, I guess grammatically that's correct, done by all of the individual forces. So we can find all the work and sum the individual work terms. And we can take the vector sum of the forces and calculate the net work and just act as if that is the only vector we need to worry about. So the work kinetic energy theorem states that the change in the kinetic energy, which is the final minus the initial, is going to be equal to the work. If you want to rewrite this such that all the terms are positive, then you just add the Ki to both sides, and you get the final kinetic energy is equal to the initial plus the net work. So the work kinetic energy theorem holds for both positive as well as negative work. So let's take a look at an example here. If the kinetic energy of a particle is initially 5 joules, a net transfer of 2 joules to the particle, or positive work, what happens? What is the final kinetic energy? And
7.
that's right, because we're transferring 2 joules to the particle. Started out with 5. If I have $5 and give you another $2, and you end up with $7. So what happens if you have a net transfer of 2 joules from the particle? Negative work.
You just subtract it.
That's right. And you end up with 3 joules. All right. So we've got a particle that moves along the x-axis. And does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity changes? And then it lists A, B, and A and B. And then in each situation, is the work done on the particle positive, negative, or zero? So let's take a look at this. Does the kinetic energy of the particle increase, decrease, or remain the same if the velocity changes from -3 meters per second to -2? Does our kinetic energy increase or does it decrease?
It decreases
Okay, why is that the case?
because it's going down, so it's not having any like energy adding in. That makes sense.
Yeah, you're getting the idea there. The velocity is decreasing, or at least the magnitude of the velocity is decreasing. So when you take a number and you square it, um, the number, if you're squaring a smaller number, then you're going to end up with a smaller result, which means in this case, since the velocity is what's being squared, then your kinetic energy is going to be smaller. So yes, that's correct. What about part B here? If the velocity changes from -2 meters per second to 2 meters per second. I'll let you know straight away that this is a little bit of a tricky question.
It'll stay the same.
That's right. Because what happens when you square -2 or you square 2?
They're equal to 4.
That's right. It's equal to the same. The mass hasn't changed. That 1/2 certainly hasn't changed. So your kinetic energy is going to be the same in both cases. The direction is going to change, but in terms of energy, there's no difference, right?
Yeah.
So that's the takeaway from this, is that if you square the magnitudes of these things, or even if one is positive and the other is negative, that the energy is not going to change. So for part C here, is the work done on the particle positive, negative, or zero? Let's take a look at part A. Since the energy is decreasing, is energy being transferred to the object, or is it being transferred away from the object?
away from the object?
That's right. And when energy is being transferred away from the object, what do we define the work as? Is it positive or negative?
Negative.
Negative, that's right. So what about part B here? Was there any difference in the kinetic energy?
No.
No. And if there's no difference in the kinetic energy, then is there any positive work or any negative work?
No, there's nothing. There's
Yeah.
no work.
No work. Okay, so work done by a gravitational force. So we're going to calculate the work as we would for any force. Our calculation here for the work done by gravitational force is going to be mgd cosine theta. If you go back and if you look at the definition of work, it's going to be the dot product of force and distance. So in this particular case, the force part of equation 712 there is going to be what? Dot in here other than just to do that for distance. So F is going to be equal to what? Mass times gravity. Force is always going to be equal to mass times acceleration. And in this case, the acceleration is going to be called what? In this case, it'll be called gravity. That's our acceleration. And if we spell this out, the dot product becomes force times distance, which means that we're going to have a cosine of the angle in between those two vectors, which is also going to be included. So let's okay. A little further. For a rising object, the angle between the distance, which is actually going to be pointing down. Let's see if I can annotate this. Distance is actually going to be pointed down because the object is going to be moving up. So the angle from here to here is going to be 180 degrees. When you put that in here, cosine of 180 degrees ends up being -1. So for a rising object, the work done by gravity is going to be negative, and it's going to be mgd. For a falling object, the force vector here, let's see, I should actually write that there. The force vector and the direction vector are going to be pointing in the same way. The angle between them is going to be considered to be 0. If you take the cosine of 0, it's 1. So the work done by the gravitational force is going to be mass times gravity times distance. That'll be positive. Does that make sense?
Yes.
Okay. So work done in lifting or lowering an object, applying an upwards force. So the change in the kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. is going to be the work done by the acceleration of the object plus the work done by gravity. For stationary objects, the kinetic energy is going to be 0, which means the work done by one is going to be the same as minus the work done by the other. So when we apply a lifting force, that lifting force, or the work of that lifting force, is going to be considered to be minus mgd cosine of theta. So work done in lifting and lowering K final is equal to K initial. And this applies regardless of the path. It doesn't matter how you get there. It's that distance in that direction. That's what matters. So let's take a look here. In this figure, we're going to show the orientation of forces and their associated works for upward and downward displacement. So note that the works in 716 need not be equal. They are only equal if the initial and final kinetic energies are equal. And if the works are unequal, you will need to know the difference between initial and final kinetic energy to solve. So let me kind of step in here. So here we got an object. We've got a force being applied to it. And then that force going up is going to be doing positive work. It's actually going to be giving it energy. And we're also considering this to be upward displacement. And the force of gravity, as defined this way, if we're defining the displacement as being up, force of gravity is going to do negative work, because if you take the dot product between those two, you'll end up with a negative answer. However, if for some reason we want to take the displacement and define it this way, since this force is moving alongside the displacement in this direction, that's going to be considered doing positive work. The force pointing upward, trying to lift it, is going to be defined as doing negative work because it's 180 degrees out of phase here. So it all depends on your definition and how you start out. So say you are a passenger and you're being pulled up a ski slope. You've got, I guess, apparently you're Santa Claus, and you've got Rudolph here. Can't really see the red nose, but I assume it's there. So you've got a tension in this rope that will do positive work. And then you've got gravity, which is going to be doing negative work. So the displacement going up this way is defined this way. And what that helps you to see is that the tension in the rope being pulled this way, that is why it is being defined as positive work, because that tension is pulling you in the direction of the displacement. Gravity, however, is seeking to pull you back down. And if you look at the component that lies in the opposite direction here, this is going to do negative work because it's working against the direction of positive displacement. This vector of the gravity here does not apply because it's perpendicular to the displacement. So let's say you're a passenger in an elevator car and you're being lowered down in an elevator. The tension is going to be considered doing negative work because you're going down or wanting to go down. Gravity here is doing positive work on the elevator car. The tension in the rope or the cable is actually doing negative work because it's working against that displacement. Okay. Have you done any work with springs up to this point?
We did some work in calculus with them, and then I remember doing them in high school.
Okay. So you may have some background to draw on for this.
Mhm.
So a spring force is the variable force from a spring. Big surprise there. Spring force has a particular mathematical form, and many forces in nature also have the same form. So we study it to kind of get an idea as to how this can be modeled. And if we find other forces that can follow the same model, then so much the better. So figure A shows the spring in a relaxed state. Since it is neither compressed nor extended, no force is being applied. In other words, the spring has no tendency in this model right here. It doesn't have any tendency to pull in or push out. It is considered to be at equilibrium. We're going to be doing work with springs and having an equilibrium assigned as x is equal to 0 and that the force is equal to 0 at that point is going to be kind of a standard. So we've got a block that's attached to the spring. Now, figure A shows it in the relaxed state. If we stretch or extend the spring, it resists and exerts a restoring force that attempts to return the spring to its relaxed state. The point is, it always wants to get back here. And if you pull it too much, what's the spring's reaction going to be? The spring is going to want to pull this block this way, right? And the reason is it doesn't like being extended out this far. It wants to be here. You've pulled it back here. So once you let go, what's going to happen to this thing?
It's gonna spring back.
That's right. It's going to head back in the opposite direction. The same type of thing is going to be true here. If you take that block and you push it in and compress the spring, it's not going to like that either. So what happens when you let go? What's going to happen to the block?
It'll spring back in the opposite direction.
Yeah, it's going to spring back and it wants to be closer here to 0. So the spring force here is going to be given by Hooke's law. And the spring force is going to be defined as minus K times the displacement. So the negative sign represents that the force is always in the opposite, always opposes the displacement. The spring constant is a measure of the stiffness of the spring. This is going to be considered a variable force. In other words, it's going to depend, the greater the force, with the greater the displacement. And as we look at it, it's going to be a linear relationship between F and D. So for a spring along the x-axis, we're going to write F of x is equal to minus kx. That's how it'll be represented. So have you seen an integral like equation 7-23 before?
Yes.
Okay, so this really doesn't come as much of a surprise here, that the work done by the spring is going to be the integral of the force times the displacement from the initial position to the final position. If you plug in kx for the force, because that's the spring force, that's what we're going to be using, and we find out that the work done by the spring is going to be 1/2 k x sub I squared minus 1/2 sub k x of f squared. The work here can be positive or negative, and it just depends on how the energy is transferred. So the spring force work, or the spring work on the spring, is positive if the block ends up closer to the relaxed position than it was initially. It's going to be considered negative if the block ends up further away. And it's 0 if the block ends up the same distance from x is equal to 0. So for an initial position of x is equal to 0, then the work by the spring is going to be 1/2 kx squared, k being the displacement. For an applied force, the initial and final kinetic energies are 0. Then the work done with the acceleration is going to be equal to the same as minus the work done by the spring. So if a block that is attached to a spring is stationary before and after displacement, then the work done on it by the applied force displacing it is the negative of the work done by the spring force. In other words, the spring work is going to cancel out any work that's done to accelerate that block. So for these three situations, the initial and final positions respectively along the x-axis for the block in figure 7.10. So in other words, this guy right here. So the initial and final positions along the x-axis for the block are -3 and then 2, 2 and then 3, and then -2 and 2. In each situation is the work done by the spring force on the block positive, negative, or 0. What you have to look for here is the block closer to equilibrium, its equilibrium position after the block was moved, or is it further away? If the block is closer, then the work done by the spring force is going to be considered positive. If, however, the block is further away, then the work done by the spring force is going to be considered negative. So in part A, is the work done by the spring force, is that going to be considered positive or negative?
Positive, because it'll be closer to 0.
That's right. What about for part B?
Negative, because it'll be far away from 0.
That's right. And what about part C?
Oh, it'll be 0.
That's right. All right, so work done by a general variable force. So we're going to look in just one dimension, and what we're going to do here is we're going to take a force, and we're going to plot that here as a function of x, and we're going to have our x value over here. So this is going to be x, and you can think of this as y, it's or a function of x. And the work is equal to the area under the curve from the initial up to the final. Does any of that look familiar?
Yes.
Okay. When we integrate force times distance, which essentially is what we've got going on here, when we integrate that area there, then what we're actually finding is the work. So as you had seen before, work is going to be equal to x of f and x of I of f of x times d of x. And if you have it going in several different dimensions or perhaps radially, this is how this is going to appear. Have you had Cal 2 or Cal 3 yet?
I'm taking Calc 2 right now.
Cal 2. So my guess is you're probably working with integration by parts and then eventually going on to sequences and series, right?
Yes, we just did like parts.
Okay.
I think.
UdV is equal to UV minus VDU. That if that doesn't sound familiar, it will. So the work and kinetic energy theorem here still applies. So power. Power is going to be the rate of time at which a force does work. In other words, how much work can you apply to something, over a set amount of time? The more work that you can apply through a set amount of time, the more power you have. And that's what this definition is saying. A force does W work in a time delta T. The average power due to the force is going to be the work times that change in time. If you want the instantaneous power, then you just take the derivative. The SI unit for power is going to be called the watt. And then work energy can be written as power times time. In other words, a kilowatt hour. Do you pay your electric bill?
Yes.
Okay. So you probably see on your electric bill, or you can look at it the next time that you do, you can see the number of kilowatt hours that you've used. That is a unit of power. Or I guess it's work dash energy. Well, that's interchangeable. So I guess it would be just work of power. Anyway. So solve for the instantaneous power using the definition of work. So if you've got power as the derivative work with respect to time, you know how work is defined: F times X and times the cosine of the angle between them. You can pull out the F, consider that to be a constant, and then you've got cosine, the variable between them, times dx over dt. Dx over dt is the change in position with respect to time. That's just the same thing as velocity. In other words, power is the same as the force dotted with the velocity. So a block moves with uniform circular motion because a cord tied to the block is anchored at the center of the circle. Is the power due to the force on the block from the cord positive, negative, or zero? To get an idea on this one, it might be helpful to kind of draw some things. So you got a block. And then you've got, your force, which is going in this way. And then you've got your velocity, which is pointed out this way. So what's the angle between those two?
90?
That's right. And because that is 90 degrees, what's the cosine of 90 degrees?
0.
0. So if you were to multiply all that together, this term is 0, which means the rest of this disappears, which means that the power due to the force on that block is always going to be 0. All right. So the summary for this particular chapter is kinetic energy. It's represented by that. Work is going to be energy transferred to or from an object via a force, and it can be positive or negative. Work done by a constant force is going to be the force times the displacement times the cosine of phi. And then you've got force times, or force dot displacement, and the net work is the sum of the individual works. Work and kinetic energy, the work is going to be the same as the change in the kinetic energy. This is just that formula rearranged. If you look at the work done by a gravitational force, it's going to be mgd times the cosine of theta. The applied work by the applied force plus the work by gravity is going to be considered to be 0. So those two oppose one another. Talked about the spring force and how that's denoted. And for an initial position, then the work done by the spring force is going to be related in this fashion. Work done by a variable force is just going to be the integration of f of x times dx. And then we discussed power, which is how much work you can apply in a set amount of time. If you're looking for instantaneous, it's going to be the derivative. And for a force acting on a moving object, it's going to be F dot V. That will denote your power. Okay. Do you want a small break before we continue?
Sure.
Okay. Why don't we have a 10-minute break? That'll give me a chance to kind of get some water from my throat. And I can see you back here in about 10, maybe 15 minutes. Sound good?
Oh, yeah, that sounds good.
Okay. All right. So we've been over chapter 7. So now we're going to get into chapter 8, which is potential energy and the conservation of energy. This week is going to be the last week here, I believe, at least for a while, where we'll be covering 2 chapters in a week. I think from now on, the majority of this is just going to be one chapter a week. It was the only way that I could get all of the material in for the entire course. So I figured it might be a little easier to sort of get used to 2 chapters at the beginning and then sort of ease off after this. So I'm sorry about that. All right, potential energy. So potential energy is going to be the energy that can be associated with the configuration of a system of objects that exert forces on one another. A system of objects may be Earth and the bungee jumper. Gravitational potential energy accounts for kinetic energy increase during the fall. Elastic potential energy accounts for the deceleration by the bungee cord, which will pull on you so you don't hit your head. Physics determines how potential energy is calculated to account for stored energy. So for an object that's being raised or lowered, the change in potential energy is going to be the same as the negative of the amount of work. So the change in gravitational potential energy is the negative of the work done. It also applies to an elastic block spring system. So here we have a couple of cases where you have negative work done by the gravitational force. The reason being the tomato, which is what this is supposed to be, is traveling upwards. It's traveling upwards. Again, remember the displacement in cases like gravity should be pointing this direction. And since the gravitational force is pulling this way and the object's moving this way, they're 180 degrees out of phase. So this is going to be considered negative work. But once it goes up and hits its apex and then starts to fall down, then the gravitational force starts to do positive work. The same type of thing is true here with the spring, where if you have the spring being pushed in. You're having, let's see, I believe in this case that the spring is doing negative work or positive work, and then as it is released, it should be changing that potential energy into kinetic energy. So that should be positive. So this would be negative, and that would be positive. The key points: the system consists of two or more objects. A force acts between a particle and the rest of the system. When the configuration changes, the force does work, changing kinetic energy into another form. When the configuration change is reversed, the force reverses the energy transfer, doing work 2, which I don't know if they ever labeled them on here or not. They didn't. So thus the kinetic energy of the tomato or block becomes potential and then becomes kinetic energy again. In other words, it oscillates between kinetic and potential energy. So conservative forces are forces for which the work 1, which is the change of kinetic energy into another form, is going to be equal to minus W2, where the force reverses the energy transfer, doing work 2. So in other words, this is going to be equal to the negative of the other. So we have just seen 2 examples of conservative forces. One is the gravitational force and the other is the spring force. Otherwise, we can't speak about potential energies. Not all forces are conservative, in which the work done in one part is equal to minus the work done in the other part. Kinetic friction is one of those. Drag force is another. Kinetic energy of a moving particle is transferred to heat by friction. Thermal energy cannot be recovered back into kinetic energy of the object via the friction force. Therefore, the force is not conservative. Thermal energy is not the same as potential energy. There's the difference here between a conservative force and non-conservative force. A conservative force around a closed path is something we're going to be looking at here. When only conservative forces act on a particle, many problems can be simplified. The net work done by a conservative force on a particle moving around a closed path is going to be 0. What that means is that the work done by a conservative force on a particle moving between 2 points doesn't depend on the path. Conservative forces are not path dependent. Non-conservative forces such as friction are path dependent. There's a real easy way to look about that, because if I take a box and I scoot it across the floor, the amount of force that I have to exhibit it is not true that any path that I take from getting from one point to the other, I'm going to have to exert the same amount of force. If the frictional force is very much dependent on which path that I take, because if I take twice the length to get to where I need to go, then I have been in contact with the floor twice as long as what I would have with another path. And because of that, the amount of friction, which would turn some of the energy into thermal energy or heat, is much more. So that is considered to be non-conservative. So if we look at diagram A here in figure 8-4, the force is considered to be conservative. Any choice between the path between the points gives the same amount of work. In other words, it doesn't matter how you get there. And if you go from A to B to back to A again, then the total work that's done is going to be the same. That's for a conservative force. So mathematically, the work going from A to B on long path 1 is going to be the same as the work going from A to B along path 2. So that result allows you to substitute a simpler path for a more complex one if you only have conservative forces involved, which can make your computations a lot easier. So the gravitational force is considered to be conservative. Any choice of the path between A and B, between those points is going to give you the same amount of work. It doesn't matter here if this block, and that kind of looks like cheese, but I don't know if that's cheese. If it were to coast along that particular line to point B, is going to do the exact same amount of work as going from here and then going down here. Both are going to be the same as far as gravity is concerned, because that's considered to be conservative. So take a look at the figure, and that figure is going to show 3 paths connecting A and B. 3 different ways to get to A and B. A single force does the indicated work on a particle moving along each path in the indicated direction. From this graph, or from this drawing, is the force conservative?
No.
Okay, why is that the case?
Because they're not going in like the same direction.
It's not so much the direction, but let me help you out here. If I take this path and I follow it from A to B, how much work or energy is involved with that?
60.
That's right, 60 joules. If I were to go from B to A, how much energy is involved there?
60 joules.
Right. If I go from A to B in this direction, how much
It's
energy?
negative.
That's right, it's negative 60 joules. Because of that, the path that I would take here would cost me energy, but the path that I would take going this direction, I would actually gain energy. So, given that, what can we say? The paths from A to B have different size. One shows the formation. One pair of paths would show a formation of a 0 work loop, and the other doesn't. So in other words, if I were to go from B to A and then back around to B again, that wouldn't cost me anything. But if I were to start at B and go this direction and then come back around this way, that's going to cost me 120 joules. So if that's the case, then the amount of energy expended going this way is different from what I have going this way. They have to be the same in order to be considered conservative. And in this particular case, it isn't. So that's the point of that particular exercise. So again, for the general case, you calculate work by saying it's the integral of f of x dx. So since work is the same as, or minus W is the same as the change in the potential energy, you can calculate the potential energy as saying the change in U is equal to minus the definition of work, which in this case is that integral. if you go through and use that to calculate the gravitational potential energy relative to a reference configuration, then you find out that the potential energy is the same as mgy. In other words, the force times your distance above y sub I, which is going to be 0 in this case. So the gravitational potential energy associated with a particle Earth system depends only on the vertical position y of the particle relative to the reference position y sub 0. Doesn't matter how far you move side to side. It just matters how far above the Earth you are. With that in mind, if you use the same methodology with springs and calculating potential energy, then the change in the potential energy is going to be equal to minus the definition of work, which in this case is f of x dx. If it's a spring, we know what that force is. That's going to be minus kx. We substitute that in, do the integral, and we find out that the change is going to be equal to 1/2 kx squared evaluated at the limits. If we just decide that our reference point for the initial position is going to be 0 for a relaxed spring, then our potential energy is going to be 1/2 kx squared. So checkpoint 2. A particle is to move along an x-axis from x is equal to 0 to x sub 1, while a conservative force directed along the x-axis acts on the particle. The figure shows 3 situations in which the x component of that force varies with x. The force has the same magnitude, or same maximum magnitude, F1, in all 3 situations. So rank the situations according to the change in the associated potential energy during the particle's motion, most positive first. So this one's going to be a tough one. This is a tougher exercise, but the key point here is that a positive force is going to do positive work. Let's see if we can find. So positive force is going to do positive work. What that means is the more positive work you have, the more of a decrease you have in the potential energy. Since the question is asking here to rank the situations according to the change in the associated potential energy, then you're going to be looking at having number 3 be the first in line. Since it has a negative force, it's going to do negative work and it's going to increase the potential energy most positively first, because your force down here is negative. The answer that will follow next is going to be 1, because the force here, while it is positive, it does decrease over time. And even though, according to our definitions here, which hopefully I haven't rushed past, this is going to generate positive work, which is going to be a negative potential energy. This particular situation is going to produce far less of a drain in potential energy than this does. Because what this graph is saying is that it doesn't matter how far over you go towards x, the force is always going to be constant. This is saying that the positive force is going to get smaller and smaller and smaller the more the faster or the closer that you get to x1. So this is going to fall off faster and produce less of a detraction in potential energy than this would. So that's why it's ranked 3, which produces a positive potential energy, than 1, which is going to drain potential energy, but not by as much, as a constant force all along, no matter where you are away from that equilibrium position. So this is kind of a tough thing to see, but that's what it's trying to explain. So conservation of mechanical energy. Mechanical energy of a system is going to be the sum of the potential energy and the kinetic energy. Work done by conservative forces increases K and decreases the potential energy by that amount. So the change, the positive change in the kinetic energy is going to be the same as the negative change in the potential energy. And if you want to go through and use subscripts, then the sum of the kinetic plus the potential energy of the second situation should be equal to the sum of the kinetic plus the potential energy of the first situation. If this mechanical energy is going to be conserved all the way through, then the sum has to hold. Now, how it gets divided is sort of up to the situation, but the sum should end up being the same. This leads us to the principle of the conservation of mechanical energy. So the change in mechanical energy is going to be the same as a change in the kinetic plus a change in the potential, which should be, it should even out. It should be 0. So when the mechanical energy of a system is conserved, we can relate the sum of kinetic energy and potential energy of one instant to that of another instant without considering the intermediate motion and without finding the work done by one of the forces involved. One way to do that is to choose the lowest point in the system as potential energy of 0. And then at the highest point where the potential energy is at the maximum and the kinetic energy is at the minimum. So let's take a look at this. This figure is showing 4 different situations. One in which an initially stationary block is dropped, and 3 in which it slides down some sort of incline. So let's rank the situations according to the kinetic energy of the block at point B, greatest first. And then part B, rank them according to the speed of the block at point B, with the greatest first. Now, all 4 of these situations are talking about either a block being dropped or they're being slid down some sort of frictionless ramp. Since we don't have friction involved and they're not talking about a drag force or anything else like that, what the answer is telling us here is that we have no non-conservative forces. In other words, everything is considered to be conservative. Energy is just going to change form. We're not going to see it dissipate. Because of that, all of the difference in potential energy must go into kinetic energy. So as the block falls, be it on one of the ramps or as it just in free fall without a ramp, in order to rank the situations according to the kinetic energy at of each block at point B, each one of them is going to have the same energy at that point. So all of these blocks are going to have the same kinetic energy at that point. In order to be able to rank them according to speed, if they all have the same kinetic energy, and if it's all the same block, which is going to have the same mass, what can we say about the velocity?
That it's also the same?
That's right. It's also the same. So how do we relate potential energy to some of the other concepts that we've had so far? Well, for a one dimension, force and potential energy are related as the following. The force in the x direction is going to be the same as the derivative with respect to x of the potential energy, or the negative of that. You can kind of see that. Let's see what page is that. That's 24. You can kind of see that back here. If you take the derivative of this with respect to x, it undoes the integral. You have the negative sign, and you just have f of x there. So because of this, we can find the force f of x from a plot of the potential energy by taking the derivative of the slope, which, since you're in Cal 2, you should be pretty well familiar with that. Taking the derivative of a line gives you the slope of that line.
Yes.
Yeah. So if we write the mechanical energy out, then we've got the mechanical energy is equal to the potential plus the kinetic, both of which are a function of x. We see how the kinetic energy varies with the potential, and they, in this case, subtract the potential from both sides. So to find the kinetic energy at any place, we can take the total mechanical energy and subtract the potential. Places where k is equal to 0 are considered to be turning points. In other words, those are areas in which the particle changes direction, because we can't have negative kinetic energy. We can have none, but we can't have negative. At equilibrium points, the slope of the potential energy is going to be 0. A particle in neutral equilibrium is stationary with a potential energy only, and a net force is equal to 0. And if it's displaced to one side slightly, it would remain in its new position. So what this is saying is an example might be a marble on a flat tabletop. If you move it to one side or whatnot, it's pretty much just going to try to remain where it is. Particle is in unstable equilibrium. It is going to be stationary with potential energy only and a net force equal to 0. If it's displaced slightly in one direction, it's going to feel a force propelling it in that direction. So let's say a marble balanced on a bowling ball, which I've never tried. But if that marble is there and stationary, it's not going anywhere. But if you push it in one direction, it's going to continue on in that direction. If you've got a particle in stable equilibrium, and that's stationary with potential energy only, and net force is equal to 0. If displaced to one side slightly, it'll feel a force returning it to its initial position. So imagine that a marble is placed at the bottom of a bowl. If you try to push it up to the side, it's just going to return back to where it was. So we'll go through some of these graphs here. So here we have a plot, and let me zoom in a little bit more. We've got a plot of the potential energy versus position. So we have our potential energy values, and then it plummets here, comes back up a little bit, goes back down here, and then levels off. Force is going to be equal to the negative of the slope. So if we take a tangent line here, and we start drawing how that tangent line looks, and then we take the negative of that, this is the graph we're going to end up with. So we've got strong force here in the positive x direction. We'll have over here between, and that exists between x sub 1 and x sub 2, as you can kind of see that as it falls off here, the force starts to get bigger. As we depart from x2 and try to work our way over to x3, we're seeing the potential energy start to increase. That is because our force, while it becomes negative, starts to level off and come back up. So you can see as you look at the points here, and then imagine a tangent line to that, you can see where these points come from. So the flat line shows a given value of total mechanical energy. Let's say that energy is going to be 5 joules. The difference between the total energy and the potential energy is going to be considered to be the kinetic. So if this is our potential, this is our total, then the difference here is going to be considered to be kinetic. And that's what meets our definition here of kinetic or mechanical energy. So at this particular point, this point right here, x sub 1, k is 0. Again, if we go back and look at our definition of k is equal to 0, no potential energy, that means it's a turning point. The particle can't go back up this way. It doesn't have enough energy to do it. If we were to follow the ball over this way, then we're going to see at this particular position that k is the greatest. That's the distance here between this and this along the energy axis here. So our particle will be moving the fastest at this time. Over here, the particle only has 1 joule of kinetic energy, so it'll be moving fairly slow compared to what it would be here. So for either of the 3 choices for mechanical energy to be here, here, or here, the particle ends up being trapped. And if the mechanical energy is equal to 1 joule, it gets trapped here. If the mechanical energy is 3 joules, then it gets either trapped over here or over here. And then if it's 4 joules, that's pretty much the same effect as well. It could end up being right here if it were 4 joules. It's just if it received any force at all, it would fall over to the other side. So, all right, this figure gives the potential energy function for a system in which a particle is in one-dimensional motion. So let's rank the regions AB, BC, and CD according to the magnitude of the force on the particle. So and then finally, what is the direction of the force when the particle is in region AB? So let's rank the region from here to here, then here to here, and then here to here, according to the magnitude of the force on the particle. If we, obviously you can see the answers here, but let's take a look and let's see why. Our potential energy here is going to be going substantially up. And can you tell me how the potential energy and the force are related to each other? So that's 29. Let's go back and let's look at the definition here. Force is going to be equal to minus the derivative of this. If that's the case, then force in this particular case is going to be the slope of this particular line. And here we're simply interested in the magnitude of that particular force. So if the force of this particular line is going to be the slope, Is that a pretty steep slope compared to what we see here and what we see here?
Yes.
Yeah, we're just comparing the magnitude, not the direction. So the magnitude of this slope is going to be the greatest. That's why that answer ends up there at the front. How does this slope compare to the slope here? Is this slope greater than what we see here, just looking at the magnitude, not the direction?
Yes.
Yes. So that's why we end up with AB here and then BC here. This slope is going to be a lot taller or a lot greater than this, and this slope is going to be greater than this one. So what is the direction of the force when the particle is in region AB? If we're in the region AB, that means our potential energy is decreasing. If our potential energy is decreasing, what's happening to our force? It should be increasing, right?
Yes.
And if it's in, because they work in opposite directions, and because it's increasing, it will be pushing this thing out to the right. It'll be pushing in the same direction as this X. This is maybe a little bit of a hard question, but that's what it's driving at. So we can extend work on an object to work on a system. Work is going to be energy transferred to or from a system. And let me decrease the size of the slide here. Work is going to be energy transferred to or from a system by means of an external force acting on that system. So for a system of more than one particle, work can change both kinetic and potential energies or other forms of energy of the system. If we remove friction, then a work is going to be defined as the change in kinetic plus the change in potential. And in shorthand, work is just going to be the change of the mechanical energy. So let's say we have a ball earth system. If we were to lift the ball here, the lifting force transfers energy to both the kinetic and potential energy. In other words, if we took not only the ball, but also the system, and we moved it up, we're changing both kinetic and potential energy as well. So for a system with friction, because obviously we have to model this at some point, we have to introduce friction. So the change in thermal energy by sliding is going to be the same as the friction, the kinetic friction force applied in the direction of displacement. We can also see that the work is going to be equal to the change in the mechanical energy plus the change in the thermal energy. And thermal energy comes from the forming and breaking of the welds between the sliding surfaces. I don't know if you've ever seen surfaces that appear to be smooth at our level of perception, but if you put them under a microscope, you can see that there are many crags, hills and valleys there along the surfaces, and those welds will combine with anything that's put close to it, and that is what causes the energy to be transferred into thermal energy, the heat. So the applied force is going to supply energy. The frictional force transfers some of it to thermal energy. So we've got a block here. We're forcing it to go this way. We've got our initial velocity, and then we've got our final velocity. This is the displacement. As the block moves along, the kinetic friction is going to work against that. So the work done by the applied force goes both into kinetic energy, which puts the block into motion, but it's also going to be thermal energy, where it starts to heat up because it's in contact with the other surface. This is going to be considered to be the block floor system. So in 3 trials, a block is pushed by a horizontal applied force across a floor that is not frictionless. The magnitudes F of the applied force and the result of the pushing of the block's speed are given in the table. So in other words, the first trial, trial A, we've got a frictional force we've got a force of 5 newtons being applied, and the block speed decreases. If we apply 7 newtons, then it remains constant. If we apply 8, then it increases. In all 3 trials, the block is pushed to the same distance. So rank the 3 trials according to the change in the thermal energy of the block and floor that occurs in that distance d, with the greatest first. And what the answer is attempting to communicate here is that all trials result in equal thermal energy change. The reason being, the value of the kinetic force of friction is going to be the same in all cases, because this coefficient only has one value. That coefficient of friction speaks to the coefficient of those 2 different surfaces being put together. So the trials here and the force and the result in the block speed really have little to do with this, because in each one of these cases, that same coefficient of friction is being applied to the normal force on the block, and the block doesn't change in each one of these trials. The amount of force being applied here does, but the normal force does not, because the block never changes its weight. Energy transferred between systems can always be accounted for. The law of conservation of energy concerns the total energy of a system. That's going to include all different forms of energy, be it mechanical, thermal, or other types of internal energy, perhaps rotation, something of that sort. You can only change by amounts of energy that are transferred to or from system. That's why we call it the law of conservation of energy. Considering only energy transfer through work, work is going to be the same as a change in energy, be it mechanical, thermal, or internal. An isolated system is just that. It's a system that doesn't come in contact with anything else. The total energy of the isolated system can't change. However, you can change from mechanical to thermal, or thermal to internal, internal to thermal, however you want to do it. That depends on the mechanisms that are going on within that particular system. So in an isolated system, we can relate the total energy at one instant to the total energy at another instant without considering the energies at intermediate times. External forces can act on a system without doing work, such as a skater here. She's pushing up against the rail. She's applying a force, or the forces from the rail is being applied to her. And so her push on the rail causes a transfer of internal energy in the form of her biceps into kinetic energy. Now she's moving. So you've got the force that's being applied there. You've got the velocity going over here, the displacement headed this way. Her kinetic energy is caused by the force from the wall, which is pushing back on her. But the wall doesn't provide her any energy. It's just that she's now in motion, And any total energy that she had is now changing forms. Since work is defined in terms of energy, if we want to expand the definition of power, we can say not only is the work divided by the time going to be considered to be power, we're going to consider the change in energy with respect to time. We're going to call that power. And again, here we also have instantaneous power as being the instantaneous change in energy with respect to time. Okay, so again, we have several different summaries here. I've made these lecture notes available so you can go back and review them. Do you have any questions at this point?
I just have a question about the lab.
Yeah.
Where do we like turn it in? Do we like send it to you like through email, or is there a specific spot on Canvas to turn it in?
There's really not a specific spot there, just email it.
Okay. And it's just like everybody emails you, right?
Yeah, I had figured all you guys would probably be working together on this, but if you're not, then you can just submit it individually. I just figured it might be easier, but to work as a group, but I could be wrong.
Okay.
Was that it?
Yes.
Okay. All right. Well, there's a material for both chapters 7 and 8. I'll upload this a little bit later on tonight. And if you don't have anything else, I will talk to you next week.
Okay. Thank you.
All right. Thank you.